some of the chapters, are a review from the quality control. Chapter 17 was some statistical, tools like mean, average, standard deviation, right? So there was another, tool in there, confidence interval. It's a very, big topic. It's gonna take, one session, 2 sessions, but in the textbook, they just showed in one example, 2 examples, without, explaining what are those, equation. You remember we talked about the Z, scores, the Z distribution, those type of thing, and then there is a T distribution. So suddenly, all of a sudden, the textbook showed, you have to use the T distribution without, providing any information. So we're gonna skip that topic, T distribution from the chapter 17. So there will be no problem, no question about the T distribution, T score, okay? Because it's gonna take 1-2 sessions. Then we have this topic, chapter 18 from textbook. We went over it in quality control. We're gonna reduce it in one session, just a review of one example from it, and then we're gonna be done with the chapter 18 today. Next week we're gonna start chapter 19. After 19, we're gonna start a new topic, which is called design of experiment. Hopefully next Wednesday. Any question, anything about previous lecture, homework, assignment? By the way, some students were concerned about the grading when they look at the grading in the Canvas. It gives you a score, but that does not represent your final score. What I do at the end of the semester, this is going to be late. I go to Canvas, change the weight of each assignment or midterm or quizzes, something like that, because it's gonna mess up every thing. So if you want to calculate your final score now, what you want to base on the evaluation chart I provided in the syllabus. You see, for example, midterm. I'm not sure, whether it was 20% or 30%, okay? So you have that one, right? And then final, this is the way I do it, at the end of the semester, I'm gonna, take all the information from Canvas and then use this, method. So let's say this is 30% of the final grade, homework are gonna be, 50, let's say, just example. Quizzes, are gonna be, so this is gonna make it less now, 10%, right? The total now is 100%. So I look at your final, right? You get, let's say 90. You have to convert it to, this scale, which is gonna be midterm, let's say 70 multiplied by this 20. Homework, all the homework, add them up, get the one average, and then let's say 90 multiplied by 40%. So this is the equation I use. Quizzes 95 multiplied by 10%. Then add them up, all of them. That is going to be your final. Great. I could not, set up this on Canvas. I tried to change it, one quiz. Then it was 19, the scale of, I think 20. One of the quiz was 20 points. Then I wanted, to change it to 100. And what happened? I scaled it up, but the student grade was not scaled up. So for example, if you got 19 out of 20, I change, change it to 100. That 19, grade of the student stayed the same. It did not, scale up to that, 100. So what I did, and then I returned it to, 20%. So this is, the method I'm going to be using at the end of the semester. Any question? Is that clear?
So this is different from the syllabus?
Oh no, this is scale, I just made it up.
Oh, okay.
If you want to know, I have to go back. No, I'm not changing the evaluation right now.
Okay.
It's going to be, let me find it. Yeah, it is somewhere, yeah, here. Homework 20%, quizzes 10%, class activity 10%, return 25, total should be 100. And this is, you find your score, and then you see where is your score. It's, let's say, 79, so you have C plus, or 98, A plus. Makes sense? Matthew just reminded me, I remember when I was, student in university, I was talking with one of my professor, I said, how can I be, successful in my academy or in the courses? He said, if you want to be active, if you want to be successful, make sure, you are engaged in the, class activity, in the classroom. So make it in a way that if you are not in the class, one session or two sessions, your professor will notice. I've noticed, Matthew wasn't here last week. So because he's always, active, right? So be like, active in the classroom. Whenever you're not in the class, the professor will notice it, right? This is one good example. Is that clear, Okay. So let's go back to this topic. This one. By the way, I posted a video for the last lecture. I don't know what happened. Oh yeah, my Aaron said that because my camera, phone didn't have enough space, so that's why it did not, record the entire lecture. So I just recorded 14 minutes of it, So, but it's, again, I put it on, Canvas. If you have question about the normal distribution, that can be a good source. I also can put a couple of videos to help you. So control chart. Dr. Schwartz, we introduced him before in the quality control. He is known as the father of process control. He invented the control chart, and then distinguished between common causes and special cause variation. Based on the control chart, we have that ability to predict future variations based on the past observation. So very good, because you want to make sure the part you are producing are going to be in a certain size, a certain limit. If it is not in the certain limit, something went wrong, then it has to be addressed, that issue or problem. There was a quick video about Dr. Schwartz. Let's see.
In 1931, Dr. Schuhart wrote a key text which laid down the principles of statistical process control. What could be measured must be measured exactly. Control charts could show what was in statistical control and what was not.
Another important association occurred while Deming was at the Department of Agriculture. He was introduced to Walter A. Schuhart, a statistician at the Bell Laboratories. Schuhart had pioneered the concept of statistical process control and the special charts that helped to achieve it. Deming was intrigued with Schuhart's ideas and studied his methods intently. Thus began a friendship and professional association that lasted until Schuhart's death in 1967. By the time Deming went to work for the United States Bureau of the Census in 1939, he was well versed in the use of statistics to improve systems. Under his leadership, sampling techniques were used for the first time in the decennial census of 1940, vastly improving its efficiency and accuracy.
What is a control chart? It is a tool that can be used to monitor, process over time, right? It's gonna plot the process data, all the data you have, it can be average, it can be ranges between the maximum and minimum, and then detect whether there is a trend or deviation from the target. So, the main idea of the control chart is that we're going to see whether our process is in control or out of control. So this is the one control chart, and the control chart for the X bar, for the average of the samples. You have the samples, and you take an average, and then over time you're going to repeat it and plot it in this chart. This is time, and this is sample data. So this is the center line. We can find the upper limit and lower limit. So each one is going to be plotted, and then it shows one data point here, and as the process makes more data, then you can distinguish whether the process is in control. Up to here, there is no problem. As we go here, still no problem. But then we realize there are 2 points which are beyond the upper control limit. So that is going to ring a bell. Then we have to find why that happened and how we can address this issue. So, this is called, this happened because of, we have some assignable case, assignable cost. This happens because they're random, random or chance variable, temperature changes in the room, that is going to change your process, right? By 2 degrees Celsius or 2 degrees Fahrenheit. It may have some effect on the process, but it's not going to make it huge in a way that it will be out of the range. So that the room temperature change, it's going to be a chance, it's a random variation. Control chart can be used to plot X bar for the average, for the range, for S. We have variable data, right? Some of those variables that have a quantity changeable. And then we have attributes. The part might be defective, so you cannot put them in this chart. We use another chart, P chart, NP chart for those data. Another way to show it, control chart has 2 category variable charts, X bar and R chart. Attribute is going to be P chart or C chart. So if the process, you have to plot X bar chart, the control chart for X bar, as well as R, range. R means range. If you want to make sure the process is in control, both of them, both the mean, the X bar, they have to be in range, and we are going to have only chance causes. If you have assignable cause, it's going to make your process out of control. Either mean or variance will be changed. They have some effect. What is the common cause? Sometimes we call chance cause or common cause. They are used interchangeably. Common cause and chance cause. The minor fluctuation in temperature during the manufacturing process, as I said before, it can be a common cause or chance cause. Or you may have some variation in the raw material quality. You may get a part from one vendor, next time you get it from a different vendor. So these are going to be a chance, random. They should not affect the overall process significantly. Okay. What is the assignable cause? Your machine over time may have some problem. They have malfunction. So if it has malfunction, what happens? Instead of making the hole with a certain diameter, 10 millimeter, it's making 11 millimeter over after 1,000 time of production. So the target, the average was changed completely from 10 millimeter average to 11 millimeter. So this malfunction of the machine, one machine, is called assignable cause, a special cause. Another special cause might be operator. You change operator, the new operator doesn't have enough skill, so that is again assignable cause. And what is X bar? X bar is gonna track the average, right? Average of the samples over time. It will detect shift in the process mean, whether your product is becoming larger, let's say, example, or smaller than it should be. Let's say in a manufacturing process, you're making a bolt with a certain length, and it should be about 15 millimeter or 1 inch in length. Average should be 1 inch, but over time you see that length is increasing, right? The average instead of 1 inch, average goes to 1 plus minus 1 inch and 1/16. So this is the new average. So this chart tracks averages. So it means the length is increasing, right? The R chart monitors the range of the value within each sample. It detects changes in variability. Let's say you are tightening a bolt in the manufacturing. One station is going to tighten a bolt, and it has to be a certain torque, right? The average, average of all of them, it's gonna stay the same. Average of the tightening, the torque. One bolt is tightened with 10 Newton meter. The other one is tightened with 15 right? What is the average? But the average in that situation is 12.5, right, for 2 samples. But you have another case. In the next case, you tighten the bolt with, I'm gonna make that average the same. Let's say case 1. One is 10 Newton meter, the torque, right? Another bolt was 15 Newton meter. Okay, so the average X bar will be 12.5, right? Case 2. In case 2, we have, I'm gonna find 17.5, and then 7.5. The average again is 12.5. Is that right? Okay, so X bar. When we look at this chart, we see, the average stay the same. Nothing happened, right? We cannot find the problem because you see, one case was 10, the other one bolt was tightened 15. But here, look at this one. This is 7.5. This is 17.5. There is a huge change, but the average we still see the same average, 12.5. So X bar is not going to be good enough. So you have to look at the R. R here is 5, right? The difference between the maximum and minimum. 5, right? What is the R here? R here is 10. Huge difference. With R range, you can distinguish, you can track something happen. So X bar is not enough, X bar chart. You have to go further, use R chart to track those assignable causes. Make sense? That's why we need both of them. And there is another one, S or variance, chart. We'll look at it later. Okay. How can we plot this control chart? For the X bar chart, we have these equations. We have to find the maximum and minimum allowed, which is called upper control limit and control limit, the central line, and then lower control limit. So you are familiar with the equation, right? So they made this factor, this one, as a coefficient called A2, and A2 is a function of D2 and N. N is the number of samples. You don't need to calculate this based on the information, the sample size you have. You have every sample size, let's say 5. Then you go to that chart to find A2. This A2 can be used to find the upper control limit, control limit, the lower control limit. X bar, this is X double bar. That is the average of all data you have. Okay, X double bar. So that is going to be the baseline. Okay, and then plus A2 times R bar. R is a range, which we can calculate it from the range of the sample. Let's say we have batch 1, batch 1. We have 5 samples. Let's say 3 samples. then x1, x2, x3, r will be the difference between the maximum and minimum, right? This is r1, and you have the next one. Let's say this one is y1, y2, y3. So you're gonna repeat this process. Then R bar is gonna be the average of these, that, right? How many you have? R1 plus R2, and divide by number of, these, let's say, n. Okay, so that's one way to do it. The standard deviation, because the standard deviation, we can use this, R divided by D2. D2 is the, correction factor that can be obtained from the chart. We have, sigma and S, both of them are standard deviation. S for, smaller population, right? And this is for, large population. Okay. And so this is gonna be a little, estimation. It's not gonna be the accurate standard deviation. This one is gonna take a look at all the data and then calculate the standard deviation. But sometimes we don't, it's gonna be tedious to calculate the standard deviation from the entire population. That's why they use this estimate. This is estimate, okay? That's why we call it estimate of the standard deviation. And it is R divided by D2. So that was for X bar chart. For R bar, it's easier. As you see, CL is going to be R bar, right? Center line. For the upper limit, you find the D4 from the table multiplied by the R bar, and this one is going to be D3 times R bar. So you don't need to calculate this factor. No, these D4 and D3 are provided in the table. You just find those numbers based on the sample size. Okay. Any question? So this question, this problem, we have X and R. So let's say the data here are X bar and R value of 24 samples. The sample size for each row, we had 5 samples. Okay, for each set, N was 5. Whenever you go to that chart, you don't look at this number. You look at this N5, to find these factors A2, D3, D4. Okay, and our range for each set is provided 3 for the first one all the way to here. Some of them are larger, for example, this one is 9, some of them are smaller. Okay, set up the X bar chart and R bar chart. So we use this equation, you take the average of all of them. When you take average of all, that is going to be called what?
Mean.
The mean, X double bar. That one should be X bar, I forgot to put that hat up there. That is X bar for every set, for every sample. So you put this average here, X double bar, and then you find A2 from the chart, which is here. The chart N is this one, right? We need A2. A2 is this number. D2, you need D2 for which one? D2. Estimating standard deviation, R divided by D2. This one, R divided by D2. And you would need, D3 and D4 for the R chart. So you take this number and bring it to this equation, and you find upper limit and lower limit. And this, are they constant or they change?
X over Y is constant.
All of these numbers, they have to be one constant number, right? All of them. At this class, in this class, sometime because the n changes, this in this class n is constant, n is 5. But sometimes n is not gonna be always 5. It might be in one scenario, in one cases, you may have n2 in this case. This might be n5 and 3. In that case, these are not constant. They will be varied. But for this class, they will be constant. Okay, one number for the upper control limit, the central line and the lower control limit. Okay, and then we have R bar. We can get the average of all of them. Put them here. D4 times R bar, D3 times R bar. Again, these are all constant number. You get one for the entire chart. How do you plot it? Once you find a number, this is, let's say, time. This is for X bar. Okay, so you find CL, you plot it here. So it's going to be the same throughout the entire process. And then LCL and UCL. So in the class activity, I'm going to give you, it's not a huge sample, it's very small. You are gonna plot something like this on the paper, show this lines, put a dash line to show the upper limit and control limit and the lower limit. So this is for X bar, and then R, it's gonna be the same. This is CL, right? LCL, UCL. But remember, this CL and this CL is not the same. They are different. This is from this equation, and this one is from this equation, right? They are different. Okay, once we plot them, these numbers, this is for the X bar, and these are the X bar number, and these are for the first sample, the second one is there, 3 is there, 4 and 5, right? This is for each iteration. You see there are 2 points out, beyond the UCL. That is flat, red flag. Something went wrong, assignable cause happened. You have to do a root cause analysis, find out what happened, whether it was operation, malfunction of the machine. Then you also look at the R bar, R chart. This looks okay. If you have only random cause, you should not be able to predict, what's going to happen in the next data point, right? So you have this data point. If you look at this, cycle, you have like a sine wave. That also shows you there is something going on in a way that you can predict, what's going to happen at the next data point. The next data point probably is going to be here, right? So also this is not, correct. This is not something we are interested. We want to have only random, data. Okay, there are some rules, let's look at 4 of them. 1 point plot outside the 3 sigma, this one. So this is the first rule. If you find one is outside, it means a non-random pattern. This is another one. Rule 2. 2 out of 3 consecutive points, they are outside, beyond 2 sigma. 2 consecutive. Now this should not be, the rule 2, because it said 2 consecutive. This should be correct, right? 2 out of 3 consecutive. Yes. Yeah, that's right. 1, 2, 3. So these are 3 consecutive. 2 of them are within 2 sigma and 3 sigma. Make sense? So let's say this 3 or this 3. 2 of them are in the between 2 sigma and 3 sigma. That is called rule 2. There are 8 rules. I just brought I'm showing only 4 of them. Okay, 4 out of 5 consecutive points plot the distance of 1 sigma. See, these are 1 sigma. 4 out of 5. They are within this range. This is also non-random pattern. And 8 consecutive points are in one side. They are in between CL and UCL. You see, there is none on this side, other than this, within that, 8. So I'm not, asking you to memorize this rule. This is only for you to know about these rules. And these are some of the non-random patterns. Any question? So this is one class activity. We have this data, right? X1, X2. So that shows the whole, the diameter of a hole that was drilled in a carbon fiber composite, and we want to see whether they are in control or out of control. Okay. So how? You have to set up X bar chart and R chart. Correct? that, website, one of you mentioned, for the grouping, random group? Yes.